Swayam Prabha. Digital India. Educated India.
Right now we are discussing about the free body diagrams, which are very important, not only from the statics point of view, but also from the dynamics point of view. Very, very important. So you have to understand this. So today I'm going to give some lecture on this free body diagram, how you do it, and the importance of it. We are going through a very important topic of statics and dynamics, the importance of free body diagrams. So in the last class, I have defined, I'm not going to write it. A free body diagram is a graphical symbolic representation of the body. So the body can be a part of the body, a structure, element, or segment of an element in which all the other connecting bodies are removed and they're replaced by the forces they exert on the body which we are under consideration. Okay. So the importance of free body comes from the fact that we need to find out what, because from now onwards it is just not one body. We are going to consider a collection or a system of bodies which are interconnected. They're not isolated, they're interconnected, but still, and then as a system, they are going to satisfy the function to which it is made. Okay. And then we would like to find out what are the forces which are coming on each component of it. And for two reasons. One is that we would like to know whether that particular component is safe enough, okay, whether it can take that many forces. Or on the other hand, it also happens that in some cases, without analyzing the free body diagrams, we may not analyze the system itself. Okay, that which we are going to see just now. Okay, so it's a very important concept, and we, for those two reasons. So let's see. As last time I was doing one small example. So like, and also see, when you draw the free body diagram, when you isolate, if the system is under equilibrium, any part of it is under equilibrium, isolated. Okay. And so that means that when you draw the isolate, when you isolate a particular component, all other components are removed. So, and then the interaction, which becomes the action on this body, is shown as the forces. Okay. So because these are transmitting the forces between the components, so you have to put those internal forces as external forces on this body. And how that interaction takes place depends upon the nature of the contact. There are several types of contacts. One is, which you know, a block moving on. There are several interactions possible. So system of connected bodies, which I gave example of, it can be a truss structure, a number of elements welded together to form a beam, a bridge or crane or any of those things, which is a truss structure. Or even we have so many mechanisms in the mechanical point of view. Say, for example, even the scissors, which you talk about, is a small mechanism consisting of several bodies. Or it can even be a crank and connecting rod, which has some 4 components connected together. wherein the applied force, linear force, is converted to a torque. So that is the function of that. So all these machines or mechanisms, okay, are made of connected bodies. So each component will act on the other body in a certain manner depending upon the contact, okay, depending upon what type of contact you have. So there are several things which we discussed. So just to, for example, this is what which you have done a number of times. So for example, here, this is a contact between these two. And so this block is resting on this one. So if you want to isolate this block, so you have a force, and this ground is going to exert a normal force and maybe a friction force, depending on whether there's a friction or not. So these two are unknowns. And together with this, so this is called the free body diagram. So together with all the external applied forces and the internal forces come because of the removal of the other bodies. So all of them put together will keep this under equilibrium. Because to start with, it is under equilibrium. A part of it is also under equilibrium. So this is the axiom. So like this, we also have seen the pin connection. So if you have a pin connection, which we discussed, so if you have a pin connection here, so this is the connection B, and so AB and BC are connected at B with a pin, and if you remove, so this pin may be a protruding cylindrical piece on AB, which is going through a hole in the link 2. Okay, so this is link 1 and link 2. So we have seen in the last class, so because it's a cylindrical surface, at each and every point on the cylindrical surface, there is a normal reaction, and which is B radial. So all of them will go through. So this is the pin. So if we isolate it, so there is all these forces which are there pass through this one, and all of them can be transferred to this one, and which we can say the resultant force. So the resultant force will be there, and which can be in some direction, which we do not know, depends upon what kind of we have here. And what we are assuming here is that there is no friction between these two surfaces, so there is no tangential force. So as long as there is no friction, so the resultant of all these distributed forces will be one resultant force passing through the center. Okay, so whether this, if you resolve it, so you have an Rx and Ry, depends upon the kind of forces that are acting. Okay, so the important part here is that this Rx and Ry are only two components. So if you isolate this one, so that means that this will be exerting an R, and this will be exerting an opposite R on link 2. Okay, so like that, so you have several interactions, and which this is very important for you to understand what are the interactions. So you should exactly put the number of unknowns one applies on the other. Like the other day, day for yesterday, so I was even saying that, so if you have a body under equilibrium like this, so a part of it can also be considered to be under. So hypothetically, if you cut this into two parts, so any one of it is so you have this. So this we discussed last time. So I'm just repeating it so that, so you have F1, 10 or something like that. So by cutting, this is perfectly valid. So any part of it is part 1 and part 2. Each one of them is under equilibrium. And the other forces which are coming 2 on 1 may have a lot of these intermolecular forces, right? So all of them can be put as one normal force and one friction force together with a moment. So this is also important in the sense that each distributed force, okay, on all these molecules can be transferred to the center with a translational component together with a moment. So you have an N in general. I mean, if you have an in general in our arbitrary direction, which can be decomposed into a normal force and a tangential force, and together with a moment. So that's here we are introducing 3 unknowns. So by doing this, so either you have 3 equilibrium equations for this 2D body, whereas here we seem to be having 6 equilibrium equations, but you should realize that we have actually introduced 3 additional variables. So by doing this, we have not really achieved anything. So we got 3 more equilibrium equations, but then we have to introduce 3 extra unknowns. So there is nothing by cutting this solid body into 2 parts. But however, as we say, if there are special connections like a sliding of the block, or maybe two levers or two rods which are connected by a pin, so there the number of unknowns which we introduce are not 3, sometimes they're less, right? So so in that process, what happens is that if you cut the bodies into 2, you will get 3 additional equations of equilibrium. But however, what you have introduced is 2 unknowns. Okay, so this is all a very important part. So whenever you draw the free body diagram, you should realize that how many unknowns you are introducing, and also you should realize how many equations which you are getting. So what I would like to show is that a quick interactions which you will see. I'll just check. These are there in any, I think I took it from Merriam book. So can you see this internal forces when isolated? Okay, first one is, as you can see, is a connection of a cable with a beam. Okay, so this rope kind of thing, you know that it can only apply a force in the direction of the rope, okay, axial force if you call it, and it will be just one force. So on the right side you can see that rope, if it is removed from the beam, so it is replaced by a T at a certain angle theta. So similarly, a surface contact, if you, from the top cylinder, if you remove the bottom support, so that is replaced by a normal force, or 3 is just an extension of that. If you have a friction, so you also have a frictional force. So this is the roller support which I was talking the other day, is a block resting on a ground with a roller in between, so can be replaced by, so since the rolling action is between the surfaces, so if you think that it is without friction, then only a normal force N can be shown. You can remove the bottom ground and you can replace it by its action by N. Okay, then we have the sliding guide, which is a sliding on a surface, which I showed a block on a horizontal surface. So it can even be a collar sliding on a cylindrical rod, okay, or maybe a block sliding in a slot. So you will see all these applications in many of our problems. And whenever you have that, so you can remove the slot part of it, and on the block, you can replace a normal reaction. And of course, if there's a friction, then you may also have to include F. Okay, next. So these are all, please look into these things. Then we have, so this is the one which I was already analyzed, the pin connection. So the pin connection can be replaced by two forces and Rx and Ry, which I said. But why he also showed M? So this M, he showed it only because if you assume there is a friction, if there is a friction, then there is a tangential force which may, when transferred to the center, it will become a moment. So the moment M will come only if there is a friction which comes out as a tangential force and transferred to the center, it will be a moment. So that moment will be there only if there is a friction. If there is no friction, there is no moment. And then the 7 is about a built-in fixed support. So this is actually, that's what we were talking just now. The whole thing is rigid. A is a rigid connection, welded. Maybe it's grouted. If it's a concrete, it's rigidly grouted into the vertical wall. Or in the mechanical things, it can be welded to another steel member. So when you do that, what happens is that it's a rigid one. So even if you remove the beam part, so then it will be replaced by the support reactions will be replaced by an F, okay, axial force, a V, a tangential force, and a moment, okay. And you will realize, you will understand this a lot more and more as you do more examples. So similarly, there's a gravitation. So this is an interaction between the body and the earth, okay. So this interaction, if you want to isolate the body, then you have to isolate this one by showing a weight. Because if you are removing the earth, okay, and if you are writing down the free body diagram of the body, then it's replaced by a simple weight is equal to mg. And then we have a spring, probably you can see it later. A spring has an internal force which is equal to K times X. So if you remove the spring, then you can replace it by a force F is equal to Kx.
In number 7, the F is towards the right, isn't it? If we push the rod towards the wall, then the F, sorry, if we pull the rod, then the F's direction should be reversed, right?
Yeah, you are perfectly right. If you know the direction, if you know how the interaction takes place, you may do so. But even if you don't put it correctly, it doesn't matter. So when you solve all the equilibrium equation, if you put F wrong direction, so F will turn out to be negative at the time of the solution. When you solve it, F will turn out to be negative. But if you know it, you put it, so you will get a positive answer. But on the other hand, if you don't put it properly, it's still okay. As long as you put two forces, that's important. You require a force F. V is upward, we put it. Even if you put it down, it doesn't matter. Even the moment, we put it as a clockwise. Even if you put it counterclockwise at this moment, it's okay. As long as you take them into consideration while putting the equilibrium equations. Okay? You understand? So there's you're not really committing any big mistake by showing the wrong direction at this moment. But when you solve it, okay, you'll solve it by taking the direction into consideration. Okay, you understand? So it's not a big mistake, even if you show it in a opposite sense. Okay. So then the third one, this last slide, is about three-dimensional interaction. Okay. So probably we'll see this more a little later, but all the same, let me tell you, is about in a three dimension, if there is a rod is in contact it has a ball end, okay, a spherical ball at the end, welded. And if it is resting on the ground, then the simple reaction is N. But on the other hand, if you also have a friction, so there can be a tangential friction. So this F maybe it is in the plane, it's in the horizontal plane, right? So this F may be in any X direction or Y direction. So we do not know at this moment. So totally you have 3 unknowns, okay? And so similarly, we have a third one is a roller contact or a wheel support. Imagine that this is a wheel moving on the rail, okay? You know the rail, train wheels and all that. So if it is moving on a rail which is constrained to move along x-axis, so it cannot move in the lateral direction, okay, perpendicular to the rail. So that is why there is a restriction which is coming because of P. And then there is a normal vertical force N, okay? So like this, so we have a number of other interactions. I think there is a ball joint, ball and socket joint, just like your hand joint or maybe even your hip. So your shoulder joint, for example. So your shoulder joint is a kind of ball. So this ball sitting in a socket has a 3-dimensional rotation, right? So it's that end. Actually, these unknown reactions are coming because of the constraint on the motion. So this is not allowed to move in X and Y and Z direction. So obviously, the other ground should apply Rx, Ry, Rz. Okay. And then this is in the 4, it's a ball. So it is free to rotate. So only what you require is forces. But on the other hand, if it is a fixed support, imagine there is a welded joint. Okay. If it is a welded joint, okay, then what happens is that it's not even allowed to rotate. Okay. Rotate. The rotations are about X and a Y and a Z. So if all these rotations are constrained, not allowed, then you also require moments Mx and My and Mz. Okay. So like this, please spend some time, take this, and these things are there. And please look into that. And so the unknown forces which are coming because of the constraints which are applied by this, between the interacting bodies. Okay. So like this, so we have, so let's quickly see. Yesterday I was doing this problem. How do you apply? So this is which I was discussing. So here you want to know the forces which are coming on, say, the link AB and link BC, which are connected by a pin here. Okay, so these are connected by a pin here. And so similarly at A, it is connected to the vertical wall by a pin. At C, it's connected by a pin to the horizontal ground. So if you look at this is a very simple support, right? I mean, a truss. So if I draw the system of these two bodies, 1 and 2, let us say, so my system is 1 and 2 supported on the ground and acted upon by a P. And if I isolate this whole system from the supports, a vertical wall and horizontal ground here, so I need we know that at a pin, we have to replace by, say, this is FAX and FAY. And similarly here, I have FCY and FCX. So similarly, you may say that, well, maybe FCX is in this direction, maybe. Okay. So at this moment, we need not really worry as long as you show two components saying that there are, so because the resultant force can be in an arbitrary direction. So for the moment, so there are two components here and two components here. So will you be able to solve this problem? So how many unknowns are there? There's FAX, unknowns are FAX, FAY, and FCX, FCY. So these are 4 in number. And so if we invoke the equilibrium equations for the two-dimensional body, so how many we get? So you get 3. So something like Fx is 0. Okay, sigma Fy, all the forces is 0, and sigma m is 0, right? So you have 3 equilibrium equations. So you have only 3, but you have 4 unknowns. You know how to frame this, right? Fx, sigma Fx is 0. So that means that sigma Fx plus Fcx is 0, and Fy. So Fay plus Fcy minus P is 0. And the moment here can be about any arbitrary point. It can be about A, it can be about B, it can be about C. So it can be about A, B, or C. So, or any other point. Okay. So you have only 3 equations and 4 unknowns. So you will not be able to solve. Right? So what do we do? So here, the importance of free body diagrams will come unless you break the body appropriately at the joint. We have to break the two bodies at joint. So we will draw the free body diagrams of one. And so here, if you do that, you have A, so Fx, Fay, and since this is a pin joint, so remember, this is pin joint, and we say then, so this is B, right? So at B, we have again Fby and Fbx. So similarly for BD for 2, so here you have so I have to show this, and okay, so now we have drawn the free body diagram. Now you are able to solve for the unknowns. So you count the unknowns and the number of equations available to you. So if you count the number of unknowns, obviously you have introduced 2 unknowns here, Fbx and Fby. So the unknowns here, are Fax and Fay. So, and Fcx and Fcy. So these are 6 in number. And then we will get 2 equations. to sigma fx and sigma fy and m. In fact, if you want, we can even write fax plus fbx. Of course, there is an external force P here. And then we also have fay plus fby minus P is 0. Okay. And what else? The moment about A, if you want, we can put it as if this is a distance of L. So maybe you can take it about A. So as I was saying, it's a matter of your convenience. Okay. So if you take moment about A, obviously these two will not enter the equation. And it's only P times, say, L by 2. And then you have only fby times L. So this is, I took counterclockwise. Maybe you can also show here that the positive convention for moment is counterclockwise is positive. So usually. So like this, so you have three equations. And so similarly for this one, so exactly the same thing. So if you have some angle theta here and L here, so you have minus fbx and plus fcx is 0. And then we also have what else? So you have fby so you can take it about B. So if you take it about B, then you have fcy L into some cos theta. Okay, so these are three equations. So you have 3 plus 3 equations for 6 unknowns. So you can solve all these 6 and then you can get the answer. Okay, so that way it is very systematic. So you should be able to realize. Oh, what I want tomorrow is that tomorrow you just have to draw these free body diagrams and write down or at least identify the number of equations and number of unknowns. Write down this and write down this. Don't solve for tomorrow. So solution will be done next week. Okay. So like this, so you can realize that the free body diagram is a must. Without free body diagrams, you cannot solve. There is another very important thing that comes also into picture. We always break at pins or maybe even at the sliding surfaces. Why we draw? Maybe can anybody? Why we are? It's convenient for us to, if the bodies are joined by a pin, why it is convenient for us to break it at the pin is that by breaking it at pin, we are introducing two unknowns, right? If it is a pin, so obviously there is an arbitrary force which is coming and fx and fy, but we are not getting a moment. Just like we broke the body, we broke it and then we said that if you break it arbitrarily, then you require two forces and a moment. So if you break it at pin, you don't get a moment. So you are introducing only two unknowns, but in that process, you are getting three equations. You understand? So if you just consider this as a single system, you are getting only three equations. But if you break it at the pin, so you are introducing two unknowns, but then you are getting 3 and 3 equations, 6 equations. Okay, so you will be able to solve. So usually we always break it at something at a point where we introduce less number of unknowns, but we get more equations. Okay, yeah, is it clear for you? So like this, and of course, I think you know that I didn't mention it probably. If you have a body here, which is so if you consider this body, interestingly, you can reduce the number of unknowns. What did I do? I put two unknowns here and obviously two unknowns here. Okay. So this body, a link, is being subjected to forces at B and at C, right? Can you say anything about these four components? Can you simplify? It's supposed to, obviously, you have six. I mean, you can use three equations and so on. So there are four unknowns. Can be reduced in any way. A body acted upon by just two forces, one at B and one at C. Something like this one. So if you have a force here and this, say, at A and B, so we have FA and FB. So if this is in equilibrium, can you say any condition on FA and FB? Yeah, you have used it in your earlier physics problems. Can you tell me any condition on FA and FB so that the body is under equilibrium? It's only acted upon by two forces, one at A, one at B. Okay. Resolve them into two components. Okay. So there are forces along AB and their force components perpendicular to this one. What is the problem? If this is under equilibrium, so obviously these forces have to be equal and opposite. So equal and opposite forces will create a moment, though the forces in line of AB, they may get cancelled. Okay. So to impose the moment equilibrium, so this moment has to be zero. So if this moment, which is contributed by the transverse forces, if you want to make it zero, either you reduce the distance, or what else? You have to make these things zero. So these forces have to be zero. So which means that then only the moment will be zero. So that means that if you have a B and if you have an A here, so what we can definitely say is that the forces at these 2 points should be in line with AB and they should be equal and opposite. So FA is minus FB, right? And they are in line with AB. Okay. So this comes very handy whenever you have a body acted upon by only two forces. So if it is acted upon by two forces at A and B, so they have to be in line with that line joining AB and they are equal and opposite. Okay. So this is very convenient. And we also said something else. If it is acted upon by three forces, you remember? So if it is acted upon by three forces, a similar condition, can you tell me? They should be concurrent. Concurrent in the sense that they should pass through some same point. For example, if these two are going here, and if you want another force at B, the only chance is that it should be in the line. So this is some line, point D. Okay. So if you know FA and FC in these directions, so produce them where they meet. And then from that point D, you draw along B so that you get a force FB. Okay. They are concurrent. Why if they're not concurrent? Any, because I have to ask the reverse question. Also, if they are not concurrent, what happens? They will leave out a moment. Okay. So because these two can be replaced by one single force acting at D. And if this, just like this, if you apply, so the resultant force at D and the force at B should be in line to avoid the moment. Okay. So that is how, if you want, you can, if you have three forces, you can also apply this one. If you have two forces, you can apply this one. So that way, so if you want to solve this problem, okay, so what you have, this is another. So you have, say, FAX, FAY, and what else? I'm going to simplify this problem. So at this B, I know that it is acted upon by only two forces at 2 points. So the unknown force here has to be in line. So FBC should be at some angle theta. Here, it should be just along this line. So I know the direction. So because it is going from B to C at an angle of theta, it has to be, because it should be in line with BC. Anything else you can say? So if you have this, can you solve this one? Is it there? Will there be enough equations for the number of unknowns? How many unknowns are here? 3 unknowns only: FAX, FAY, and FBC. FBC, I know the direction, so it's only the magnitude that's unknown here. So here, unknowns are, so these are unknowns. And how many equations you have? How many equations you have? 3 equations. So the equilibrium equations, 3. Okay. So like this, so you can, at many places, there are many bodies which are acted upon by only 2 forces. So you can replace them. You can replace the whole equilibrium of that by a single force only, single unknown force. Okay. So this way you can, so if you have some 5-6 bodies interconnected, there are many bodies which are just 2 force members, which can be replaced by a single unknown. Okay. So we'll continue this. So please go through it. Please go through the textbook and try to appreciate these problems. Okay. I think I'll stop here.